So for this problem here, what we are trying to find is the mass of this block. Now, mass is simply density times volume. So in order to find mass, we're given the density, we need to find the volume. Well, the volume of the entire block, of the full block, would be length times width times height. That would be the 60 millimeters times the 200 millimeters times the 80 millimeters. Which would give us 960,000 millimeters cubed. But we know it's not a full block. We have this piece here that is a segment of a circle that has been machined out, that groove, or I said that segment of a circular groove that has been machined out of it. So we need to figure out what the volume of that material removed was so that we can subtract it from this total volume of the block. To find the volume of the material removed. First step we're going to have to do is find the radius of that circle. So what we're going to do is we're going to draw that out here. We have this that's 100 millimeters. And this is 30 millimeters. The rest of the circle would look something like that. We did this at the end of last semester, where we said this is going to get split in half. So 50 millimeters here and 50 millimeters over here. And then we're going to extend this up through to get a full diameter of a circle. But first we're going to find this piece here, which I'm going to call X. And if you recall the rule, these are intersecting chords of a circle. The product of the pieces of each chord are equal to each other. So this chord is 50 by 50, so it's 50 times 50. Has to equal this chord, which is 30 times X. So, of course, 50 times 50 is 2,500. And we'll divide by the 30. To get X equals 80.33333. Oops, let me try that again. 83.333 equals X. Which means the diameter of that circle is that 83.33333 for X plus the 30 equals 113.333 millimeters. And then the radius, of course, is half that. $56.667 millimeters. So we have the radius of that circle. So that means up here, this radius right here is the 56.667 millimeters. Or this would be the same over here. To find the area of the segment, remember we're looking for the area of this piece down here. We need to know two things. Remember, the area of a segment is equal to the area of the whole sector minus the area of the triangle. Well, at this point, we can find the area of the triangle. The triangle is this shape right here. It's pretty easy to find. Since we know that this is 56.667, the bottom across here is 100 total. We actually know the height here. We can confirm it, but we can find it by subtraction. I'm going to confirm it here. That height has to be the square root of 56.667 squared minus 50 squared. Remember, 50 would be halfway there. Here is 26.667. Now, I did not have to go through this use of the Pythagorean theorem because I knew that this distance from here to here was just 30 millimeters. I could have just subtracted that from my radius of 56.667 to get that 26.67. Is that coming over the PA system?
Yeah.
Okay. Oh boy.
It's a battle cry.
Anyway, it's a cry for help. So anyway, the area of that triangle then will be the 100 for the base. Times that height to 26.67 divided by 2. That gives us 1333.37 approximately. Okay, so we got 1333.37 square millimeters is the area of the triangle. Now we need to go back to find the area of the sector. Find the area of that sector. That's this shape here. What we need to know is this angle here. We already know the radius is 56.667 millimeters. To find that angle, we'll use this right triangle here where this is 50, half of the 100, and we'll find this angle right here. According to that angle, of course, the 56.667 is the hypotenuse. 50 is the opposite. Very good. Opposite and hypotenuse make the sine. Very good. Sine theta equals opposite over hypotenuse. Opposite side is 50. Our hypotenuse is 56.667. How do we find the angle?
Inverse sine.
Inverse sine. Perfect. Make sure my settings are correct here for the day. Inverse sine of 50 divided by 56.667 gives us 61.93 degrees. Now I'm going to multiply that by 2 to get the whole angle. So 123.85. Now the reason it was very important that I multiplied it without clearing the calculator is you'll notice it doesn't work out to be exact here. If I had just multiplied this, if I had typed the 61.93 back in and multiplied by 2, I would have been off by 1/100th of a degree. Not going to make a huge difference in our answer, but if you really want to be precise, try to keep that in your calculator and use it as much as you can so you don't have to write it down and type it back in. So now the area of our sector is going to be pi times 56.667 squared times what else? Our angle there of 123.85 over 360, the full circle. Giving us 3468.83. So now I have to just subtract those two. The area of the sector, the 3468.83, minus the area of that triangle of 1333.37, 2135.46. Millimeters squared is the area of that segment. So again, that is the area of this piece here, 2135.46 square millimeters. Now remember, what we were actually wanted to find was the volume of the material removed. What we found here is just an area. But we know that we can always get from an area to a volume by multiplying by a depth or a height. So our area of 2135.46 millimeters squared times the depth of that is just the 60 millimeters. This is going to go back 60 millimeters here. So giving us a volume of 128,127.6 millimeters cubed. And now we can find the volume of the block after the material is removed for that groove, that segment of a circular groove. We had the volume of the entire block before it was removed of 960,000. Millimeters cubed. Now we're going to subtract the 128,127.6 millimeters cubed for that groove that was machined out. 831,872.4 millimeters cubed is the final volume of that. However, our density, what we're trying to find here is actually the mass. And you remember the mass is density times volume. But our density is 0.24 kilograms per centimeter cubed, not millimeter cubed. So we need to first convert our volume into centimeters cubed, into cubic centimeters. So this is another throwback to last semester. From millimeters to centimeters on our chart is one spot to the left, which would normally be one decimal place if it were centimeters and millimeters. But it's not. It's cubic centimeters and cubic millimeters, which means that one spot on the chart is how many decimal places? 3, right? 10 by 10 by 10 is 1,000. That's 3 decimal places. This is 831 point, we're just going to go 8724 centimeters cubed. So our mass is our density of 0.24 kilograms. Now I'm going to write this as 0.24 kilograms over 1 centimeter cubed because that's what it really means. And the reason I'm going to write it like that is now I'm going to multiply it by 831.8724 centimeters cubed. I'm going to put that over 1. And you'll see what happens here if we do a little dimensional analysis working with our units. Basically, this is like our measurement conversions that we did last semester. You can see the cubic centimeters cancel out, and the only unit we have left is kilograms. So we're going to take the 0.24 times 831.8724 gives 199.65 kilograms would be our mass of that object. Not so bad, right? So, the key concepts that we have to remember for a problem like this. The first one is just simply that formula. Mass is density times volume. The second big formula is that area of a segment was the area of the whole sector minus the area of the triangle. Third big formula, we've used this enough, I probably don't even need to write it down, but the area of a sector is equal to the area of a circle times our angle over 360. But then the big one, the one that we wouldn't be able to do anything on this problem without, is the formula for intersecting chords. And that was this one. or if we know this length here is A, this length is B, and we're trying to find, call that X, we know that this gets split in half, A over 2. So we know that A over 2 times A over 2, or half of A times half of A, has to equal to B times X. And we can use that then to find X, that piece of that chord. And of course, from that, it follows that the diameter of the circle is X plus B. Of course, you can find the radius as half of that diameter. So realistically, we didn't do anything new today. Everything, I mean, the trig came in as far as just finding this angle here so that we could find the central angle for the area of our sector. That's where the trig came into this one. But that was just simple triangle trig doing an inverse sine to find an angle. All the other concepts that we did here were actually concepts from last fall semester, just put together in a different way in this problem. With that, actually, most of you did get the quiz turned in yesterday from before, but if not, there is a quiz out there from last week yet that all of you are missing at least. There's not a new quiz today. Let me double check. I believe it's coming up tomorrow. I take that back. Your new quiz is today. So that's out there for you to work on. And then, of course, there are actually 2 worksheets in Blackboard for today. There's one marked April 13th and the other one marked April 13th B. Both of them are examples of this exact same type of problem, just different numbers, so that you can practice. If you do one and you're doing great on it, you don't have to do the second one, but just second practice problem if you need it. So with that, I'll let you guys have our last 20 minutes here to get started on those problems. I'll be on the network here for a little while if you need any help.